Somewhere in the universe, there may be a civilization so vast it has wrapped an entire star in a shell of collectors, drinking every photon that star will ever produce. And that civilization, by one measure, would still only be halfway up the ladder. Welcome to the Sleepy Lab. Tonight, you will drift through one of the quietest and most profound frameworks ever proposed for thinking about life in the cosmos. A simple scale, 3 steps long, that stretches from a single warm planet all the way to the light of 100 billion suns. If any of this settles gently into your mind as you fall asleep, consider subscribing, one sleepy soul at a time. Now, let's begin. In 1964, a Soviet astronomer named Nikolai Kardashev sat down to think about a practical problem. Not a philosophical one. He was not asking whether alien life existed, or what it might look like, or whether it was friendly. He was asking something more specific, and in its own way, more grounded. He wanted to know how powerful an alien radio transmitter might be. If another civilization somewhere in the galaxy was broadcasting a signal, how much energy would it take to send that signal across interstellar distances? And how would we know what we were looking for? To answer that, he needed a way to think about civilizations in terms of energy, how much a civilization could command, how much it could spend, how far that spending could reach. And so he proposed a scale. 3 types. Clean, simple, almost architectural in its clarity. A Type 1 civilization has learned to use all the energy available to it on and delivered to its home planet. Every joule of sunlight that falls on its surface, every wind, every tide, every thermal gradient in the deep rock beneath its feet, all of it gathered, all of it used. This is not a civilization that has merely discovered electricity. It is a civilization that has become, in a sense, the steward of an entire world's energy budget. The total solar energy striking Earth's surface each day is roughly 10,000 times what our entire global civilization currently consumes. 10,000 times. That number is worth sitting with for a moment. We are not close to Type 1. Not yet. A Type 2 civilization has gone further. Much further. It has found a way to capture the full energy output of its parent star, not just the thin slice of starlight that happens to fall on one small planet, but everything the star produces in every direction, in every moment, across its entire lifespan. The total power of a sun-like star is roughly 10 to the power of 26 watts, a number so large it resists ordinary intuition. Freeman Dyson, a physicist writing in 1960, described one way this might be done: a vast swarm of orbital collectors, millions or billions of individual structures spread across a shell around the star, each one drinking in light and converting it to usable energy. Not a solid sphere. That would require more material than exists in all the planets of our solar system combined. But a swarm. A slow, patient, distributed net of collectors, assembled over centuries or millennia, gradually enclosing a star the way a forest gradually covers a hillside. A Dyson swarm would change how the star looks from a distance. The visible light would be absorbed and re-emitted as infrared radiation, a warm glow at longer wavelengths, a kind of thermal signature that would be, in principle, detectable by telescopes looking for anomalies in the sky. Astronomers have actually searched for this. Catalogs of infrared bright stars have been examined for exactly this kind of anomalous heat signature, the faint possibility that somewhere in the data, a star is running slightly too warm, wrapped in something we did not put there. So far, nothing confirmed. But the search continues, quietly. A Type 3 civilization has done something almost impossible to hold in the mind. It has extended its reach across an entire galaxy. Roughly 100 billion stars, each one quietly burning, each one a potential source of energy on the scale of a Type 2 civilization's entire output. And a Type 3 civilization has found a way to use them. Not necessarily all at once, not necessarily all in the same way. But the total energy available to such a civilization would be roughly 10 to the power of 36 watts, the combined luminosity of a large galaxy, flowing through whatever structures and systems that civilization has built across hundreds of thousands of light years. What would that look like from Earth? It is difficult to say with certainty. A galaxy whose stars were gradually being enclosed, one by one, would grow dimmer in visible light and brighter in infrared over millions of years. A slow transformation, almost geological in its pace, but detectable if you knew what to look for. We have looked. We have not found it. And that silence is one of the quieter mysteries in all of science. Where does Earth sit on this scale? By standard calculation, roughly type 0.73. Not yet type 1. Not even close to type 2. We are a civilization that has learned to split atoms and harness rivers and cover hillsides with solar panels. And by Kardashev's measure, we are still in the early pages of the first chapter. Carl Sagan, who extended the scale to allow for fractional values, placed us somewhere in the lower reaches of the first type, a civilization with real capability, real reach, but still drawing on only a small fraction of what our own planet receives from the sun each day. There is something humbling in that number. 0.73. Not because it is small, but because of what it implies about the distance still ahead. To reach Type 1, we would need to increase our energy use by roughly a factor of 100,000, and that is only the first step. To reach Type 2, we would need to enclose a star. To reach Type 3, we would need to fill a galaxy. Kardashev proposed his scale as a practical tool, a way to estimate the power of a transmitter, to calibrate a search. But it became something else over time. It became a kind of mirror. A way of asking not just what other civilizations might be capable of, but what we might become, given enough time, enough patience, enough survival. The scale does not tell us whether any civilization has ever reached Type 2 or Type 3. It does not tell us whether such things are possible, or whether something always intervenes before a civilization gets that far. It only tells us what the energy would look like if it happened. And it tells us, very quietly, where we stand. 0.73. Young. Still close to the ground. Still learning what a planet is worth. And yet, the sun does not wait for us to be ready. Every day, without pause, it pours energy onto this planet. Enough to dwarf everything we consume, everything we burn, everything we have ever built or powered or lit. The total solar energy reaching Earth's surface in a single day is roughly 10,000 times our entire global energy use. 10,000 times. Not in a year, in a day. We are standing in a river and drinking from a thimble. That gap between what arrives and what we use is one way of understanding where we sit on the scale, not as a judgment, simply as a measurement. A quiet statement of where the work still lies. Carl Sagan, who thought carefully about these things, felt that Kardashev's original 3 steps were too coarse, too sudden. A civilization does not leap from one type to the next overnight. It climbs, slowly, unevenly, over centuries and millennia. So Sagan extended the scale to allow for fractional values, letting civilizations be placed between the whole numbers, the way a thermometer reads between degrees. That is how we arrive at 0.73, not a rounding, a position on a continuous line. The line itself is worth sitting with for a moment. A Type 1 civilization commands roughly 10 to the power of 16 watts of continuous energy, that is 10 million billion watts, flowing without interruption. Every volcano, every ocean current, every beam of sunlight that touches the ground, all of it gathered, all of it used. A civilization at Type 1 has learned to be fully present on its world. It has closed the gap between what its planet offers and what it consumes. We are not there yet. But Type 1 is at least imaginable. It is a planetary scale. We live on a planet. The arithmetic, however daunting, is not beyond conception. Type 2 is something else entirely. A Type 2 civilization commands roughly 10 to the power of 26 watts. That is the full energy output of a sun-like star, not the light that reaches one planet. All of it, in every direction, continuously. The difference between Type 1 and Type 2 is not a matter of building more power plants or covering more desert with solar panels. It is a difference in kind. To reach Type 2, a civilization must leave its planet behind, not abandon it, but outgrow it and learn to work at stellar scales. The physicist Freeman Dyson thought carefully about what that might look like. In a paper published in 1960, he described a way a civilization might capture the full output of its star, not a solid shell. That would require more material than exists in all the planets of our solar system combined, and the structural forces involved would be impossible to manage. What Dyson described was something more elegant, a swarm, millions, perhaps billions, of individual collectors placed in orbit around the star at various distances and angles, each one intercepting a portion of the light, each one converting it to usable energy. A Dyson swarm. The name came later, but the idea was his, and it is, in its way, a deeply practical idea. It does not require exotic physics. It does not require materials we cannot imagine. It requires only time and patience and the willingness to disassemble worlds and rebuild them as something more useful. There is something quietly staggering about that image. A star, still burning at its center, surrounded by a slowly thickening cloud of human-made objects, each one small, each one purposeful. Together, they dim the star from the outside, not extinguishing it, but drinking from it, the way a civilization at 0.73 drinks from the sun, only completely, only without waste. And the star would still be there, still fusing hydrogen into helium, still doing what stars do. Only now, almost none of its light would escape into open space. It would be caught, converted, used. What would escape is heat. Any structure that absorbs energy must eventually release it in some form. A Dyson swarm, or any structure built to capture stellar light, would re-emit that energy as infrared radiation, longer wavelengths, lower temperature, invisible to the naked eye, but detectable to the right instruments. This is what astronomers call a technosignature, a sign of technology, written in the language of physics, readable across interstellar distances. A Type 3 civilization commands roughly 10 to the power of 36 watts, the luminosity of a large galaxy. 100 billion stars, or something close to it, all of their energy flowing into a single civilization's use. It is a number that resists comprehension, not because it is merely large, but because it implies a presence, a civilization spread across light years, across star systems, across the slow turning of a galactic arm. That would be, in some sense, everywhere at once. From Earth, a Type 3 civilization would not be subtle. A galaxy in which every star had been partially or fully enclosed would look different from an ordinary galaxy. Its visible light would be dimmed. Its infrared glow would be anomalously bright. The ratio of what it emits to what it should emit, given its stellar population, would be off, detectably, measurably off. We have the instruments, even now, to notice such a thing. Astronomers have searched catalogs of galaxies for exactly this kind of anomaly. So far, nothing clear has emerged. That silence is worth holding gently, without rushing to explain it. It does not mean Type 3 civilizations do not exist. It does not mean they do. It means that if they exist, they are either rare enough that none fall within our observable range, or they are somehow quieter than the physics suggests they should be, or we are not yet looking in quite the right way. The universe is large, and our search, measured against it, is still very young. But the question does not go away. It settles in, the way a question does when it has no easy answer. If a civilization could reach Type 3, if the physics allows it, if the time is sufficient, if nothing intervenes, then a galaxy-spanning civilization would be hard to miss. It would reshape the infrared sky. It would leave marks on the distribution of stars. It would be, in some sense, the galaxy. And yet, the Milky Way, as far as we can tell, is quiet. Its stars burn in their ordinary patterns. Its infrared signature matches what you would expect from a collection of stars and dust and gas, without obvious signs of large-scale engineering. Either no civilization in our galaxy has reached Type 3, or the marks are there and we have not yet learned to read them, or something about the path from here to there is harder than the scale implies. The scale, after all, only describes the destination. It says nothing about the journey. It does not account for the time required, the failures along the way, the civilizations that began the climb and did not finish it. It does not ask what a civilization must survive, or sacrifice, or become in order to move from one type to the next. It only marks the levels and leaves the space between them open and quiet and full of everything we do not yet know. That space between the levels, it is not empty. It is filled with questions the scale was never designed to answer. But there is one question the scale does invite. If a civilization reaches Type 2, if it truly masters the energy of its star, what does that actually look like? What does it look like from the outside, from a distance, from here? The most discussed answer begins with a simple observation. A star produces energy in all directions. It pours light into the void in every direction equally, indifferently, without purpose. Most of that energy travels outward and is never used by anyone. A civilization that wanted to change that would need to surround its star, to build something around it, to catch the light before it escaped. Freeman Dyson described this possibility in 1960. Not a solid shell, he was careful about that, but a swarm. Millions, perhaps billions, of individual collectors orbiting a star at various distances and angles, each one intercepting a portion of the light, each one converting that light into usable energy. A Dyson swarm. The idea is elegant in its simplicity. You do not need to build one enormous structure. You build many smaller ones over time, and the swarm grows denser as the civilization grows more capable. But a solid sphere, the version that appears most often in imagination, would require something the solar system cannot provide. To enclose a star completely in a rigid shell, you would need more raw material than exists in all the planets of our solar system combined. Every rocky world, every gas giant, Every moon and asteroid and scattered fragment of debris gathered together, melted down, reshaped, and it would still not be enough. The numbers are simply too large. The distances are simply too vast. A solid Dyson sphere, in the strictest sense, is not something a civilization builds. It is something a civilization imagines and then finds another way around. The swarm is that other way, and the swarm has a quality that makes it visible across interstellar distances. When a collector intercepts starlight, it absorbs that energy and uses it. But energy is never truly consumed. It is transformed. The waste heat from all that collection and use must go somewhere. It radiates outward as infrared light. Longer wavelengths, lower energy, invisible to the naked eye, but detectable to the right instruments. A star surrounded by a Dyson swarm would look different from a bare star. Its visible light would be dimmed, partially blocked by the collectors. But its infrared glow would be brighter than expected. Anomalously bright. Warm in a way that dust and gas alone cannot fully explain. This is what astronomers call a technosignature, a mark left on the universe by the activity of a civilization. Not a radio signal, not a deliberate message, but a consequence. A side effect of simply existing at that scale. And so astronomers have looked. They have searched through catalogs of stars, flagging the ones that shine too brightly in infrared, the ones whose thermal signatures do not quite match what ordinary stellar physics would predict. So far, nothing has held up under scrutiny. The anomalies, when examined closely, have found natural explanations. Dust shells, stellar winds, the particular chemistry of aging stars. But the search continues, quietly, in the background of other work. Because the logic is sound. If a Dyson swarm exists anywhere within range of our instruments, it should leave a trace. And one star, for a brief period, seemed to offer something. The star designated KIC 846-2852 sits roughly 1,000 light-years away in the constellation Cygnus. It came to wider attention around 2015 when researchers analyzing data from the Kepler Space Telescope noticed something unusual in its light curve. The star was dimming, not in the smooth, regular way a planet dims a star as it passes in front. That pattern is predictable, periodic, clean. This was different. The dimming was irregular. It came in clusters, at uneven intervals, with varying depths. Sometimes the star lost a few percent of its brightness. At one point, it dimmed by more than 20%. No known natural object of reasonable size could produce that pattern. The data was genuinely puzzling. And in that puzzle, some researchers allowed themselves to consider the possibility. Could this be a structure? Something built. Something in the process of being built, perhaps a swarm still growing, still incomplete, blocking the star's light in uneven patches as the collectors accumulated. The idea was raised carefully, as a hypothesis among others, not as a conclusion. But it traveled quickly, and the star acquired a name. Tabby's star, after the astronomer Tabitha Boyajian, who led the original analysis. For a time, it was the most watched star in the sky. Observers around the world coordinated to catch the next dimming event in real time, across multiple wavelengths, hoping to find a pattern that would distinguish engineering from nature. What they found, over years of careful observation, pointed away from engineering. The dimming was not uniform across wavelengths. If a solid, opaque structure were blocking the light, it would block all wavelengths equally. But the dimming was stronger at shorter wavelengths and weaker at longer ones. That is the signature of dust. Fine particles, unevenly distributed, scattering and absorbing light in the wavelength-dependent way that only small, natural grains do. The most supported explanation now involves clouds of dust and cometary debris, fragments of disrupted bodies orbiting the star in loose, irregular streams, passing between the star and our line of sight at unpredictable intervals. Not a swarm of collectors, a swarm of rubble. The star is still unusual. Its long-term dimming over decades remains an area of active study. But the extraordinary hypothesis did not survive the extraordinary scrutiny. And that is how it should work. The question was asked honestly. The data was gathered carefully. The answer, for now, is dust. And the search moves on. There are other ideas about what a Type 2 civilization might do with its star beyond simply surrounding it. One of them is stranger and quieter, and in some ways more patient than anything else proposed. It is called stellar lifting. The concept is straightforward in principle, though the engineering would be unlike anything we have attempted. A star is not a fixed object. It is a sphere of plasma, held together by gravity, constantly losing mass through its solar wind, slowly burning through its hydrogen fuel. In principle, a sufficiently capable civilization could accelerate that mass loss deliberately. Using magnetic fields, focused energy, or other mechanisms not yet fully worked out, it might be possible to draw material up from a star's outer layers and collect it. Hydrogen and helium, in quantities that dwarf anything available on planets or moons. Fuel for other purposes. Raw material for construction. Or something else entirely. Because stellar lifting also offers a different possibility. If you remove mass from a star, you change it. A less massive star burns more slowly. Its fusion rate drops. Its lifespan extends. A civilization that began lifting mass from its star early enough could, over millions or billions of years, reshape that star into something cooler, dimmer, and far longer lived, stretching a stellar lifetime that might otherwise end in 10 billion years into something that lasts 100 billion or more. The universe is old, but the stars that anchor civilizations are not permanent. They age and swell and die. And a civilization that thinks on long enough timescales might choose to tend its star the way a gardener tends something slow and irreplaceable. Not consuming it, preserving it, extending it. There is something in that image worth resting with for a moment. A civilization so patient, so far-sighted, that it plans not for centuries, but for the lifespan of a star, and works, quietly, to make that lifespan longer. And yet, that patience points somewhere further still. Because stellar lifting, taken to its conclusion, is not just about fuel or construction. It is about time. About a civilization choosing to exist across timescales that make human history feel like a single breath. And if a civilization is thinking on those scales, if it has already wrapped its star in collectors, already begun the slow work of tending its stellar flame, then it faces a question that has no small answer. What do you do with all of that energy? One answer, perhaps the most extraordinary answer anyone has proposed, is this: you think. Not metaphorically, literally. You convert the entire energy output of a star into computation. The structure imagined for this purpose has a name: a Matryoshka brain, named quietly after the nested wooden dolls, one inside another, each smaller than the last. The concept is similar, a series of concentric shells, each one surrounding the last, each one harvesting the waste heat of the shell beneath it, and using that energy to compute layer after layer after layer, all the way out until almost nothing escapes. The innermost shell runs hot, processing at high temperatures. The outer shells run cold, working more slowly but still working. Every photon that leaves the star is eventually caught, converted, used, not for motion, not for construction, not for warmth, but for thought. The total processing power available to a Matryoshka brain is, by any reasonable estimate, incomprehensible. Orders of magnitude beyond anything a biological mind can picture. Whatever consciousness or intelligence or experience might run on such a structure, it would bear no resemblance to anything we know. And yet, it would not be invisible. This is one of the quieter ironies of megastructure physics. A Matryoshka brain, for all its concealment, for all its apparent stillness, cannot hide entirely. The laws of thermodynamics do not make exceptions. Energy used for computation still produces waste heat, and that heat has to go somewhere. It radiates outward as infrared light, longer wavelengths, cooler than the star itself, but present. A star surrounded by a Matryoshka brain would look, to a distant observer, like an ordinary star that had somehow gone quiet in visible light and begun glowing strangely in the infrared. Warm where it should be cool, dim where it should be bright. Astronomers have catalogs of such anomalies. Most have mundane explanations. Dust, geometry, the ordinary complexity of stellar environments. But the search continues, quietly, in the background of other work. Because if a Matryoshka brain exists anywhere within range of our instruments, it would leave exactly this kind of trace. A whisper in the infrared. A star that is thinking and cannot quite hide the warmth of its thoughts. But not every civilization that reaches Type 2 would turn inward like that. Some might turn outward. Type 2. Energy. The full output of a star, sustained and directed, is not only enough to power computation, it is enough to move things, large things, things that, from our current vantage, seem immovable by definition. Planets. A civilization with access to stellar-scale energy could, over long enough timescales, alter the orbit of a planet. Not quickly, not in a human lifetime or 100 human lifetimes, but gradually, through repeated gravitational nudges, through directed energy, through the patient application of force across millennia, a world could be moved closer to warmth or pushed further from it. A moon could be repositioned. A comet, falling inward on a collision course, could be redirected before it ever became a threat. The solar system, seen through this lens, is not a fixed arrangement. It is a starting condition, something that can be worked with, adjusted, slowly reshaped by a civilization that has both the energy and the patience to treat geological time as a reasonable planning horizon. Entire solar systems, over millions of years, could be reorganized, not chaotically, but deliberately, the way a landscape is shaped by long, slow intention. This is what Type 2 energy actually means. When you follow it to its implications, not just power, not just light and heat, but agency over the physical structure of a civilization's home. And then there's the step beyond that. Type 3. A civilization that has not merely mastered its star, but spread outward, across the light years, from one stellar system to the next, and the next, until the entire galaxy, 100 billion stars, each one a potential energy source, each one a potential home, falls within its reach. The numbers involved are almost too large to hold, but one of them is worth sitting with. A civilization expanding at just 1% of the speed of light. Not fast. By the standards of what a Type 2 civilization might achieve, would cross the full diameter of the Milky Way in roughly 10 million years. 10 million years. It sounds long, and by human standards, it is beyond imagining. 10 million years ago, our ancestors were small, tree-dwelling creatures with no language, no fire, no stone tools. 10 million years is deep time, by any human measure. And yet, the Milky Way is roughly 13 billion years old. 10 million years is less than 0.1% of that age. It is, in the life of a galaxy, an eye blink, a brief interval, the kind of time that passes between one geological era and the next without leaving much of a mark. Which means that if even one civilization had reached Type 2 anywhere in this galaxy, even once, in the last several billion years, and had then chosen to expand, it would have had more than enough time to reach every corner of the Milky Way before our sun had even formed. And we would know. A Type 3 civilization does not hide easily. A galaxy reorganized for energy use would look different. Its stars would dim in unusual ways. Its infrared signature would shift. The distribution of stellar types might change, as some were tended and others were not. The chemistry of nebulae might carry traces of industrial processes on scales we cannot yet imagine. We have looked, not as thoroughly as we might, and not for as long as we should, but we have looked, and we have found nothing that clearly, unambiguously points to a civilization of that scale. The galaxy appears, as far as we can tell, natural, unmodified, quiet. And that quiet is one of the deepest puzzles in all of science. Not because the absence of evidence is itself evidence of absence. It is not, necessarily, but because the math is so unforgiving, the timescales are so generous, the galaxy is so old and so large, and has had so long to fill with the consequences of intelligence. And yet here we are, in a small spiral arm, around an unremarkable star, listening and hearing nothing that we can be certain of. This is not a failure of imagination. It is not a gap in our instruments, though our instruments are limited. It is a genuine puzzle, one that sits at the intersection of physics and biology and philosophy and time. If civilizations can reach Type 3, and the galaxy is old enough for dozens of them to have done so by now, where are they? The question does not have a clean answer. It may not have one answer at all, but the asking of it leads somewhere worth going, into the long, careful thinking that humans have done about why the universe might be full of possibility and yet appear, from where we stand, so very still. That thinking has a name, and it begins, as so many things do, with a quiet question asked over lunch by a physicist who already knew the answer might be unsettling. His name was Enrico Fermi, a physicist of extraordinary precision, a man who could estimate the yield of a nuclear explosion by dropping scraps of paper in the wind. He was having lunch with colleagues in the summer of 1950 at Los Alamos, and the conversation had drifted, as conversations do, toward the question of whether other intelligent life might exist somewhere out there in the universe. And then, at some point during that meal, Fermi asked a question. Where is everybody? That was it. No formal paper, no elaborate proof. Just a question, asked quietly over food, that has not stopped echoing since. The question carries weight because of what it implies. If the universe is old enough, and large enough, And if the conditions for life are not impossibly rare, then by now, by the time we're sitting here, in this particular moment, there should be evidence. Not necessarily a signal aimed at us, not necessarily a ship in the sky, but something, some trace, some consequence, some artifact of civilizations that had billions of years to grow and spread and leave their mark on the structure of things. And yet the sky is quiet. This is what we call the Fermi Paradox. Not a paradox in the strict logical sense, but a tension, a gap between what the numbers seem to suggest and what we actually observe. It is the silence that needs explaining. About a decade after that lunch, a radio astronomer named Frank Drake sat down and tried to make the question more precise. It was 1961, and Drake was preparing for a small scientific meeting on the possibility of detecting signals from other civilizations. He wanted a way to organize the problem, to lay out all the things you would need to know in order to estimate how many communicating civilizations might exist in the Milky Way right now. So he wrote an equation. It begins with the rate at which stars form in the galaxy. Then it asks what fraction of those stars have planets. Then what fraction of those planets might be capable of supporting life. Then what fraction of those actually develop life. Then intelligence. Then technology capable of sending detectable signals. And finally, how long such a civilization might remain detectable before it goes silent or disappears. Multiply all of those terms together, and you get an estimate. The difficulty is that almost none of those terms are known with any confidence. The first few, star formation rates, the prevalence of planets, have become much better understood in recent decades. But the biological and social terms remain deeply uncertain. How often does life actually arise on a world that could support it? How often does that life become complex? How often does it become curious and technological and communicative? We have exactly one data point for each of those questions: ourselves. And so the Drake equation, depending on how you fill in its terms, can yield answers ranging from less than one civilization in the entire galaxy to millions of them. Both answers are consistent with the same equation. Both answers are consistent with what we currently know. The equation is less a solution than a map of our ignorance, a careful accounting of everything we do not yet understand. One response to the silence is to suggest that we are not typical, that the conditions which produced us are not common at all, but are instead the result of an unlikely convergence of circumstances that most worlds never experience. This is sometimes called the rare Earth hypothesis. It begins with the observation that Earth is not simply a rocky planet at the right distance from a star. It is a rocky planet with a very particular set of properties, each of which may have played a role in allowing complex life to emerge and persist. Consider the Moon. Our Moon is unusually large relative to the size of Earth. Most moons in the solar system are small captured objects, or the remnants of ancient collisions. Ours is thought to have formed from a massive impact early in Earth's history, and its size has had a quiet, stabilizing effect ever since. The gravitational pull of the Moon acts as a kind of anchor on Earth's axial tilt, the angle at which our planet leans as it orbits the Sun. Without that anchor, Earth's tilt could wander significantly over millions of years. And the axial tilt is what gives us our seasons, what drives the circulation of the atmosphere and the oceans, what shapes the long-term patterns of climate across geological time. A planet whose tilt drifts unpredictably might experience swings of temperature so severe, so prolonged, that the slow work of evolution, the patient accumulation of complexity over billions of years, might be interrupted, or reversed, or never allowed to begin in earnest. We do not know how many planets have large moons. We do not know how many of those moons formed in the right way, at the right size to provide this kind of stability. It may be common, it may be rare. As far as we can tell, it is one of many factors that made Earth what it is, and we cannot yet say how often the universe arranges things this way. The Moon is only one piece of it. There is also the position of Jupiter, sitting far out in the solar system, its gravity quietly deflecting many of the objects that might otherwise have struck the inner planets more frequently. There is Earth's position within the galaxy itself, far enough from the dense, radiation-intense center to allow stable chemistry, but not so far out that the raw materials for complexity were unavailable. There is the presence of liquid water, maintained over billions of years by a combination of distance from the sun, atmospheric pressure, and geological activity that recycles carbon and keeps the climate from drifting too far in either direction. Each of these factors, taken alone, might not seem decisive, but together, they suggest that Earth may occupy a narrow region of possibility, a place where many things went right, in sequence, over an enormous span of time. If that is true, if worlds like ours are genuinely uncommon, then the silence of the universe becomes less puzzling. Not because intelligent life is impossible elsewhere, but because the path to it may be longer and more contingent than it first appears. And yet, the rare Earth hypothesis is not universally accepted. Some researchers argue that life is more robust than we assume, that it finds ways to emerge and persist under conditions we would consider hostile, that our one example has made us too conservative in our estimates. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, and many of those stars have planets. Even a very small probability, applied to numbers that large, can produce a very large result. The silence remains. And so the question stays open, not as a source of anxiety, but as a genuine invitation to think carefully about what we are, and where we came from, and how unusual or ordinary that might be in the larger context of things. We are a civilization that has existed in any recognizable technological form for only a few thousand years. We have been listening to the sky with radio telescopes for less than a century. Our radio bubble, the sphere of signals we have sent outward into space, is only about 200 light years across, containing a few thousand stars out of hundreds of billions. In the scale of the galaxy, we have barely whispered. It is possible that the universe is full of quiet things, each one listening, each one too young or too small or too brief to have yet found the others, like lights coming on, one by one, in a very large and very dark room, each one unaware of how many others are beginning to glow. And yet, even that image, lights coming on in a dark room, carries a quiet assumption worth examining. It assumes the room is ready for lights. It assumes the conditions that allow a civilization to exist at all are common enough that many such lights should be flickering on around the same time. That may not be true. Consider our own position in the solar system, and how many things had to be arranged just so. Jupiter, the largest planet in our neighborhood, sits in an orbit that has, over billions of years, acted as a kind of gravitational shepherd. Its enormous mass deflects and captures many of the objects that would otherwise fall inward toward the rocky planets. The inner solar system has still been struck many times, and those impacts have shaped the history of life here in profound ways. But the rate of large impacts may have been lower than it would have been without Jupiter's presence. A slightly different arrangement of the outer planets, and the story of life on Earth might have been interrupted more often, or more completely. This is not certain. Planetary dynamics are complex, and some researchers have questioned how protective Jupiter's influence truly is, but the possibility is worth sitting with. Then there is the question of where we sit within the galaxy itself. The Milky Way is not uniform. Near its center, stars are packed more densely, and the environment is more violent. Higher radiation, more frequent supernovae, gravitational disruptions that could destabilize planetary orbits over time. The galactic center is not a hospitable neighborhood for the slow, patient chemistry that life seems to require. Earth orbits at a comfortable distance from all of that, far enough from the center to avoid the worst of the radiation and the chaos, close enough to the galactic plane to have access to the heavier elements that stars in the outer reaches sometimes lack. This region, sometimes called the galactic habitable zone, may be one of the more favorable addresses in the Milky Way for a world like ours. And yet, even granting all of this, the right star, the right planet, the right position in the galaxy, the right neighbors, there is still a deeper question. Why, given a universe 13 billion years old, do we not see clear evidence of civilizations that have had far longer than we have to develop? One answer is the Great Filter. The idea is this: somewhere along the path from simple chemistry to a spacefaring civilization, there is a step, perhaps more than one, that is extraordinarily difficult to pass. Not merely unlikely, but nearly impossible. A filter so fine that almost everything is stopped by it, and almost nothing gets through. The filter could be behind us. The emergence of life from non-living chemistry is still not well understood. It happened here, apparently, within a few 100 million years of Earth's formation, which is fast, on geological timescales. But we do not know whether that was easy or whether we were simply fortunate. The transition from simple single-celled life to cells with a nucleus, the kind of complex cell that eventually gave rise to all plants and animals, took roughly 2 billion years after life first appeared. 2 billion years of single-celled life before that one improbable step. And then, hundreds of millions of years more before anything resembling an animal existed. Each of these transitions could be the filter, or the filter could be something even earlier, the formation of a planet with liquid water, or the emergence of a stable genetic code, or some other threshold we have not yet identified. If the filter is behind us, if the hard part is already done, then we may be among the first complex civilizations in the universe. The silence around us would not be a mystery. It would simply be the silence of a universe that has not yet had time to fill with voices like ours. That would be, in its way, a remarkable thing to be. But there is another possibility. The filter may lie ahead. If the emergence of life is common, and the development of intelligence is common, and civilizations arise regularly across the galaxy, and yet we see no evidence of any of them, then something must be stopping them. Something that acts on nearly all of them before they become visible, before they reach the kind of scale that would leave unmistakable marks on the cosmos. A Type 2 civilization, capturing the full energy of its star, would be detectable. A Type 3 civilization, spreading across a galaxy, would be unmistakable. If such civilizations existed in any significant number, we would likely know. The absence of that evidence, in a universe old enough to have produced them many times over, is itself a kind of data. It suggests that the path from where we are now to where a Type 2 civilization stands may be one that very few, if any, have completed. The filter ahead could take many forms: self-destruction through war, or ecological collapse, or the development of technologies that outpace the wisdom to use them carefully. It could be something more subtle, a tendency for complex civilizations to turn inward, to find satisfaction in virtual or internal worlds rather than expanding outward. It could be something we have not imagined. We do not know. And here is where the science becomes genuinely uncomfortable. If we were to find life on Mars, not ancient traces, Not ambiguous chemistry, but actual living microbes. However simple that discovery would be, paradoxically unsettling. Not because life on Mars would be unwelcome, but because of what it would imply. If life arose independently on two planets in the same solar system, then life is probably not rare. It probably emerges wherever conditions allow, with some regularity, across the universe. And if life is common, then the great filter is probably not in the emergence of life. It is somewhere further along the path, which means it is somewhere ahead of us. The more common life turns out to be, the more the silence of the cosmos points towards something that stops civilizations after they begin, rather than before. This is why some researchers have said, quietly, that they hope the Mars rovers find nothing, not out of indifference to discovery, but out of a clear-eyed understanding of what a positive result would mean for the long-term prospects of civilizations like ours. It is a strange position to be in, hoping that a neighboring world is barren, because barrenness would be the more reassuring answer. And yet, even this framing carries uncertainty. The Great Filter is a hypothesis, not a confirmed feature of the universe. It is one way of making sense of the silence, not the only way. The silence may have other explanations, observational limits, the vast distances involved, the possibility that advanced civilizations are simply very quiet, or that we are looking for the wrong signs in the wrong places. What the Great Filter does, more than anything, is ask us to take the silence seriously, not to explain it away too quickly, not to assume that the absence of evidence is simply a gap in our instruments. The universe is old. The conditions for life have existed in many places for a very long time. If the path forward is open and easy, we should expect company. The quiet around us suggests the path may be neither, and we are still on it. One explanation, quiet but persistent, is that civilizations do not survive long enough to be found, not because the universe is hostile to them from the outside, but because they become hostile to themselves. War is the most obvious version of this idea. A civilization that develops the means to split atoms, to engineer pathogens, to build weapons of cascading consequence, may not always develop the wisdom to restrain those means in time. The gap between capability and judgment may be the most dangerous interval in a civilization's life. Ecological collapse is another form of the same pattern. A civilization that consumes its planet faster than the planet can recover may find itself stranded, technologically capable, but resource depleted, unable to make the leap to the next level before the foundation beneath it gives way. And then there is the quieter possibility of runaway technology, systems that grow beyond the intentions of their creators, or that redirect a civilization's energy inward into simulation or consumption rather than outward toward the stars. None of these are certainties. They are patterns that can be observed in small ways, in early stages, and extrapolated with some unease into the longer arc of what civilizations tend to do with power. If any one of these filters is common enough, the galaxy could be full of civilizations that rose, reached a certain threshold, and then went silent. Not because they were destroyed from without, but because something within them gave way. The silence, in this reading, is not emptiness. It is the accumulated quiet of many endings. And yet, there is another possibility, one that does not require destruction at all. It is called the dark forest theory, and it begins with a different kind of logic. The idea is this: any civilization capable of detecting another civilization must also recognize that it cannot know that civilization's intentions. Resources are finite. The universe is vast, and communication is slow. In a situation of deep uncertainty, with survival at stake, The rational response may be to eliminate any potential threat before it can grow into an actual one. If this logic is universal, if every civilization that reaches a certain level of awareness arrives at the same cold calculation, then the galaxy would not be full of civilizations reaching out to one another. It would be full of civilizations hiding, carefully, deliberately, erasing every signal that might betray their presence. In this picture, the silence is not absence. It is concealment. Civilizations are there. They're simply very careful not to be found. This is a deeply unsettling idea, and it is worth sitting with that discomfort gently rather than pushing it away. It implies that our own early radio transmissions, already spreading outward at the speed of light, may have been a kind of inadvertent announcement, one that a sufficiently cautious observer might view with concern. It is not a proven theory. It is a logical structure built on assumptions about scarcity and fear that may or may not apply to minds very different from our own. But it is one coherent answer to the silence, and it has a certain cold internal consistency. A softer version of the same idea is sometimes called the zoo hypothesis. Here, the civilizations are not hiding from each other out of fear. They are hiding from us, specifically out of something closer to restraint. The idea is that one or more advanced civilizations are aware of Earth, aware of us, and have chosen not to interfere, observing from a distance, the way a careful naturalist might watch a young species without disturbing its development. There may even be, in this hypothesis, something like a protocol, an agreement among older civilizations not to make contact until a younger one has reached some threshold of technology, of stability, of readiness. It is a gentler picture than the dark forest, but it carries its own strangeness. It means the silence around us would be, in some sense, curated, maintained. A deliberate gift, or a deliberate withholding, depending on how one chooses to read it. Neither of these ideas can currently be tested. They are frameworks for thinking about the silence, not explanations with evidence behind them. What they share is the assumption that the civilizations exist and that their absence from our awareness is a choice rather than a fact. There is one more possibility, stranger still. The simulation hypothesis asks whether advanced civilizations might exist not in the physical universe at all, but within it, inside computational substrates of their own construction, running at scales and speeds that bear no resemblance to the world we can observe. A civilization that has reached Type 2 or Type 3 energy use would have access to processing power that is, by any ordinary measure, almost incomprehensible. The question of whether such a civilization would choose to inhabit physical space, or whether it might find the interior of a sufficiently complex computation more hospitable, more expansive, more interesting. That question does not have an obvious answer. If civilizations tend, at some point in their development, to migrate inward rather than outward, into simulated realities rather than physical ones, they would become, for all practical purposes, invisible to any telescope we could build. They would not emit the signatures we are looking for, because they would no longer be doing the things that produce those signatures. This is speculative in the deepest sense. It touches on questions about the nature of mind and reality that physics alone cannot resolve. But it is worth noting that it offers a coherent answer to the silence that does not require destruction, concealment, or rarity. It simply requires a different direction of travel than the one we have assumed. And this brings us, gently, to the question of what we are actually looking for when we search the sky. The word for it is technosignatures. A technosignature is any detectable sign that technology exists somewhere, any pattern in the data that cannot be explained by natural processes alone. Radio signals are the most familiar kind. But the category is much broader than that. Light pollution leaking from a planet's night side, the chemical fingerprints of industrial processes in an atmosphere, the infrared excess of a star whose light has been partially captured and re-emitted by orbital structures. Any of these, if detected, would be a sign that something is building, burning, processing, existing in a way that nature alone does not produce. One of the more concrete possibilities involves nitrogen dioxide. In Earth's atmosphere, nitrogen dioxide occurs naturally, but industrial combustion produces it in concentrations well above the natural baseline. A planet with elevated nitrogen dioxide, detectable in the spectrum of its atmosphere, would be a quiet but significant signal, not proof of intelligence, but a reason to look more carefully. The James Webb Space Telescope has already demonstrated the ability to analyze the atmospheric chemistry of planets orbiting distant stars. It is not yet sensitive enough to detect nitrogen dioxide at the concentrations we are imagining, but the capability is no longer theoretical. It is a matter of refinement, of time, of better instruments built on the foundation of the ones we already have. We are, for the first time in the history of this planet, building tools that could, in principle, detect the atmospheric consequences of another civilization's industry, not their intentions, not their art, not their inner life, but the chemical residue of their energy use, drifting through the light of a distant star. It is a modest beginning, but it is a beginning. The universe is very large, and we have been listening, in earnest, for only a very short time. The silence so far is real, and it is also, perhaps, simply the silence of a search that has barely started. Consider, for a moment, how young our search really is. We have been sending radio signals into space for roughly 100 years. 100 years of transmission, spreading outward at the speed of light, forms a sphere. That sphere is about 200 light years across. 200 light years sounds vast. And yet, the Milky Way contains somewhere between 200 billion and 400 billion stars. Our radio bubble, that entire century of human transmission, encompasses only a few thousand of them, a few thousand out of hundreds of billions. It is less than a single grain of sand on a very long beach. Less than that. Even. If another civilization were listening from the far side of the galaxy, they would have no way of knowing we exist. Our signals have not reached them. They may never reach them. Not in any meaningful time frame. The galaxy is simply too large, and we have been speaking for too short a time. This is worth sitting with quietly. The silence we observe is not necessarily the silence of an empty universe. It may be the silence of a universe in which everyone is too far apart and too new to the act of listening to have found each other yet. Our radio bubble is vanishingly small, not a failure of the cosmos to answer, but a reminder of how little of it we have actually touched. And so the search continues, widening slowly, instrument by instrument, year by year. The James Webb Space Telescope represents a different kind of reach, not radio, not the active transmission of signals, but the quiet reading of starlight. When a planet passes in front of its star, a small fraction of that starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths. What arrives at our telescopes carries the chemical fingerprint of whatever that atmosphere contains. Webb has already demonstrated this capability. It has detected carbon dioxide, water vapor, sulfur dioxide in the atmospheres of planets orbiting other stars. These are not nearby planets. Some are hundreds of light years away, and yet the chemistry of their skies is becoming, slowly, legible to us. The era of reading other worlds from a distance has begun. It is still early. The concentrations of gases we could hope to detect as technosignatures, nitrogen dioxide at industrial levels, for instance, remain at the edge of what current instruments can resolve, but the foundation is laid. Future telescopes, larger and more sensitive, will build on what Webb has established. The question of whether another world's atmosphere carries the residue of industry is no longer purely philosophical. It is, in principle, answerable, and that is a quiet but significant shift in what it means to search. There is another approach to reaching across the distances of space, not with signals, but with physical objects. A civilization that has mastered its star's full energy output, a Type 2 civilization, would have access to power on a scale difficult to hold in the mind. Roughly 10 to the power of 26 watts, continuously available, the entire luminosity of a sun. With that kind of energy, certain things become possible that are otherwise only theoretical. One of them is directed energy propulsion. The idea is straightforward in principle, though staggering in scale. A powerful laser, or an array of lasers, focused on a lightweight sail attached to a small probe. The pressure of light itself, concentrated and sustained, accelerates the sail to a significant fraction of the speed of light. At 1% of light speed, the nearest star system, Alpha Centauri, about 4.25 light-years away, would be reachable in roughly 400 years. At 10 or 20% of light speed, that journey shortens to decades. Not a human lifetime, but within the span of a civilization's patience. A Type 2 civilization, drawing on the full output of its star, could sustain such a beam continuously. The energy cost, measured against what it has available, would be manageable. It could, in principle, send probes to neighboring stars, receive data back across the years, and build a picture of the galaxy one system at a time. This is not science fiction in the sense of being impossible. The physics is understood. The engineering is far beyond us now, but not beyond what the laws of nature permit. Projects like Breakthrough Starshot have already explored scaled-down versions of this concept, imagining gram-scale sails pushed by ground-based lasers toward Alpha Centauri within a human lifetime. A Type 2 civilization would not need to imagine it at a small scale. It could do it properly. And if it could do it properly, it could do it repeatedly. Probes to dozens of stars, then hundreds, then thousands. Each one a quiet ambassador, carrying instruments, perhaps carrying something more. Over millions of years, a civilization with that capability and that patience could map the galaxy in extraordinary detail. Which returns us, gently, to the question that has been resting beneath all of this. If such civilizations are possible, and the physics suggests they are, where are they? The Milky Way is roughly 13 billion years old. The first stars formed not long after the universe itself began. The heavy elements needed for rocky planets and complex chemistry took time to accumulate, scattered by generations of stellar death. But by several billion years ago, the conditions for life as we know it were already present in many parts of the galaxy. A civilization that emerged even a billion years before us would have had a billion years to develop, to climb the Kardashev scale, to spread, if it chose to spread, across the stars. At even 1% of light speed, a civilization could cross the entire Milky Way in roughly 10 million years. 10 million years is a long time by human standards. It is less than 0.1% of the galaxy's age. A civilization with a billion-year head start could have crossed the galaxy nearly 100 times over. And yet, we see no clear sign of them. No Dyson swarms detected in our stellar catalogs. Those searches have been conducted. No unmistakable technosignatures in the infrared surveys. No signals in the radio frequencies we have monitored. No probes in our solar system that we have found. The absence is not absolute. It is possible we have missed things. It is possible the signs are there and we have not yet learned to read them. Our searches have been limited in scope, in duration, in the range of signatures we know to look for. But the absence is real enough to ask why. This is the heart of what Enrico Fermi reportedly asked during a lunch conversation in 1950, in a question that has carried his name ever since. If the universe is old and large, and the conditions for life are not extraordinarily rare, then where is everyone? There is no single answer. There may never be a single answer. But there are several quiet possibilities, each worth considering in turn. One is simply scale and time. Our radio bubble is a few thousand stars out of hundreds of billions. Our searches have covered a small fraction of the sky at a limited range of frequencies for a few decades. The silence so far may mean very little. We may be like a person standing in a vast forest at dawn, having listened for only a few seconds, concluding the forest is empty because no bird is called in that moment. The search has barely started, and the forest is very, very large. Another possibility is distance. Not just the distance between stars, but the sheer unhurried scale of what crossing that distance would require. The nearest star system to our own is Alpha Centauri, a little over 4 light years away. At the speeds our fastest spacecraft currently travel, reaching it would take roughly 20,000 years. 20,000 years ago, humans were painting animals on cave walls and following herds across frozen plains. The idea of sustaining a journey of that length, across that emptiness, with any technology we currently possess, is not a failure of imagination. It is simply an honest accounting of how far away everything is. And Alpha Centauri is our neighbor. The stars beyond it are farther still, and the galaxy stretches on for 100,000 light years in every direction. Even a civilization far more capable than our own would face the same fundamental arithmetic. Space is not merely large, it is large in a way that resists crossing, that absorbs effort, that turns ambition into patience. A Type 2 civilization, one that commands the full energy of its star, might find ways to work with this distance rather than against it. One such method involves a phenomenon called gravitational lensing. When light passes close to a massive object, gravity bends its path, and that bending can act like a lens, focusing and amplifying what lies beyond. Our own sun has a gravitational focus point, located roughly 550 astronomical units from its center, far beyond the outer planets, but not impossibly far for a civilization with the means to reach it. From that vantage, a telescope could use the sun itself as an optical instrument of extraordinary power, capable of resolving fine detail on planets orbiting other stars. A civilization that had mastered its own solar system might position observatories at that focal point and spend centuries quietly mapping the surfaces of distant worlds, not visiting them, simply watching, learning which ones hold liquid water, which ones carry the chemical signatures of biology, which ones glow faintly with the light of cities at night. A Type 3 civilization, one spread across an entire galaxy, might do something similar on a far grander scale. The dense mass at the galactic core creates a gravitational lens of almost incomprehensible power. A civilization that understood how to use it could, in principle, communicate or observe across the full diameter of the Milky Way, 100,000 light years, with a clarity that no conventional telescope could approach. The galaxy itself would become an instrument. Whether any civilization has ever done this, we cannot say, but it is worth sitting with the image for a moment. A network of minds, spread across 100 billion stars, using the gravity of their shared galaxy to speak to one another across distances that would otherwise swallow any signal into silence. And yet, even this picture raises a quiet question. Where would such a civilization have begun? One answer that astronomers have considered involves a particular kind of stellar neighborhood, the globular clusters. These are ancient, densely packed spheres of stars, some containing hundreds of thousands of suns bound together by gravity, orbiting the outskirts of galaxies like slow, luminous satellites. The Milky Way has over 100 of them. What makes globular clusters worth considering is their age. The stars within them are, on average, around 10 billion years old. Some are older still. Earth and its sun are roughly 4.5 billion years old, which means that life in a globular cluster, if it arose, would have had a head start of several billion years over anything that emerged here. Several billion years is a span of time that is genuinely difficult to hold in the mind. It is longer than the entire history of complex life on Earth, multiplied many times over. A civilization that had been developing for that long, even slowly, even with long pauses and setbacks, might have reached a kind of depth and stability that we can barely gesture toward. The silence from globular clusters, if there is life there, would be a different kind of silence. Not the silence of absence, but perhaps the silence of patience, of a civilization that has long since stopped broadcasting into the void and found other ways to exist. But there is a complication. Globular clusters are old in a way that carries a cost. The stars that formed them did so early in the universe's history, when the raw materials available were mostly hydrogen and helium, the lightest elements, the ones that emerged from the first moments after the Big Bang. The heavier elements, carbon, oxygen, iron, silicon, the building blocks of rocky planets and complex chemistry and biology, those were forged later, inside stars that lived and died across billions of years, scattering their contents outward through supernovae. Globular clusters formed before much of that scattering had occurred. Their stars are, by the measure astronomers use, metal poor, meaning they contain relatively few of the heavier elements that planets like Earth are made of. A solar system forming in a globular cluster might have less raw material available for rocky worlds. The chemistry available to any life that arose there might be simpler, more constrained. Whether this rules out complex life entirely is not settled. It makes it harder, perhaps significantly harder. But the universe has a way of finding paths that careful reasoning does not always anticipate, and the question remains genuinely open. So globular clusters present a kind of tension, ancient enough to have given life an extraordinary head start, but perhaps not rich enough in the right materials to have made that life easy to begin. It is a tension without a clean resolution. And that, in a way, is characteristic of almost every thread in this inquiry. Each possibility opens onto another uncertainty. Each answer carries a quiet asterisk. The scale of the universe, the age of its oldest structures, the chemistry required for complexity, the distances that separate everything from everything else. These are not obstacles that imagination can simply dissolve. They are real features of the cosmos, and any honest account of where we stand has to hold them steadily. We are a young civilization, on a young planet, orbiting a middle-aged star, in a galaxy that has been forming stars for over 10 billion years. We have been listening for a few decades. We have been capable of sending signals for roughly a century. Our reach, measured against the size of what surrounds us, is very small. And the universe, for all its age, may still be early in the story of complexity. The conditions that allowed something like us to exist, the right elements, the right stellar neighborhood, the right planetary stability, may have only recently become common enough to matter. If that is true, then the silence is not a mystery to be solved, but a condition to be understood. The quiet of a cosmos that is only now, in its old age, beginning to wake. The nearest star is 20,000 years away at our current pace. The galaxy is 100,000 light years wide. And somewhere in all of that, in the ancient light of globular clusters, in the gravitational geometry of galactic cores, in the infrared warmth of stars that burn a little differently than they should, there may be answers we have not yet learned to read, or there may simply be more quiet, patient, vast, and very old. And yet, within that quiet, there are events so violent that the word violent barely holds them. There are moments in the universe when a single object releases more energy in 10 seconds than our sun will produce across its entire life. 10 billion years of steady burning against 10 seconds. When a massive star exhausts its fuel and collapses, the core falls inward so rapidly that the rebound sends a shockwave outward through the star's outer layers. The core itself compresses into something almost incomprehensible. A neutron star, a sphere perhaps 20 kilometers across, containing more mass than the sun, spinning sometimes hundreds of times per second. In those first 10 seconds of its existence, the energy released, mostly as neutrinos, particles so small they pass through ordinary matter almost without noticing it, exceeds what our sun will quietly radiate across all of its remaining years. The sun is not a small thing. It is 1,000,000 times the volume of Earth. It has been burning for 4.5 billion years and will burn for roughly 5 billion more. And yet a neutron star, in its first moments, outpaces it by a measure that is difficult to hold in the mind. This is not sensationalism. It is simply what the physics describes. A neutron star that forms spinning rapidly carries an enormous reservoir of rotational energy. It slows over time, radiating that energy away. But in its youth, it spins with a kind of stored power that a sufficiently advanced civilization might, in principle, find useful. There is a concept, loosely borrowed from the physics of rotating black holes, sometimes called a Penrose process analog. Around a spinning black hole, there exists a region where space itself is dragged along by the rotation. A theoretical object entering that region could, under the right conditions, extract some of that rotational energy and leave with more than it arrived with. The black hole slows slightly. The object carries away the difference. A neutron star is not a black hole, but it is dense enough and spinning fast enough that similar principles have been proposed. A Type 2 or Type 3 civilization, patient and capable of engineering at scales we cannot yet approach, might find in a spinning neutron star not a catastrophe but a resource, a compact, ancient engine radiating its stored motion into whatever structure surrounds it. We do not know how such a structure would be built. We do not know if the physics would cooperate in the ways the theory suggests, but the proposal exists, quietly, in the literature. A civilization that has mastered stellar energy might eventually look further, toward the most extreme objects the universe produces, and ask what can be drawn from them. And if we follow that line of thinking far enough, we arrive at a boundary. The total luminosity of the observable universe, every star, every galaxy, every quasar, every process that releases energy across the 13 billion light-year sphere we can in principle observe, amounts to roughly 10 to the power of 49 watts. That number is the ceiling, not a practical ceiling, not a ceiling imposed by engineering or politics or the limits of any particular civilization, but a physical one, the absolute upper bound on what any conceivable civilization could ever command. If it somehow harnessed every source of energy in everything we can see. Some theorists have added a fourth level to the Kardashev scale to name this possibility. A Type 4 civilization would draw on the energy of the entire observable universe. Not a star, not a galaxy. Everything. It is worth sitting with that for a moment. A Type 1 civilization controls a planet. A Type 2 controls a star. A Type 3 controls a galaxy of 100 billion stars. And a Type 4 would stand in relation to a Type 3 the way a Type 3 stands in relation to us. We are, by the standard calculation, at roughly 0.73. The distance between where we are and Type 4 is not a distance that can be meaningfully described in familiar terms. It is more like the difference between a single candle and the sky on a clear night, multiplied by itself several times over. And yet the scale exists. The physics permits it, at least in principle. Whether anything in the universe has ever approached it is a question that may never have an answer we can verify. There is, however, a complication. The universe contains something we do not fully understand, something that makes up roughly 68% of its total energy content. It is called dark energy, and it is responsible for the fact that the universe is not merely expanding, but accelerating in its expansion. Galaxies are moving apart from one another, and they are doing so faster and faster as time passes. Dark energy is not a fuel in any sense we currently understand. We cannot collect it, concentrate it, or direct it. We can observe its effects, the redshift of distant galaxies, the geometry of the cosmic microwave background, the rate at which large structures form, but we have no mechanism for accessing what it represents. It is, in a sense, the largest energy reservoir in existence, and it is entirely beyond reach, at least for now, at least with any physics we currently possess. A Type 4 civilization, if such a thing could exist, would presumably require access to something like it. But how that access might work, or whether it is even theoretically possible, remains genuinely open. And dark energy introduces another constraint, one that applies even to civilizations far more capable than us. As the universe expands, the space between distant galaxies grows. Beyond a certain distance, that expansion is fast enough that the light from those galaxies can no longer reach us. They are not moving through space faster than light. That would violate what we know. But the space between us and them is growing faster than light can cross it. The effect is the same. They become permanently unreachable. This boundary is called the cosmological event horizon, and it means that even a Type 3 civilization, capable of traveling at a significant fraction of light speed, spreading across its galaxy, and perhaps beyond, would eventually find itself confined. The galaxies it could not reach in time would simply recede beyond contact, one by one, over billions of years. In roughly 100 billion years, the Milky Way and the small cluster of galaxies gravitationally bound to it, the local group, will be the only galaxies visible from our position. Everything else will have crossed the horizon, not destroyed, simply gone from reach. A civilization that does not expand beyond its local gravitational island before that horizon closes will be confined to it permanently, not by any failure of technology or will, but by the geometry of an expanding universe. This is one of the quieter implications of cosmology, that time itself imposes limits, that the window for certain kinds of expansion is not infinite, that the universe, for all its age, is also in some sense running. And so the Kardashev scale, which began as a practical tool for estimating the power of alien radio transmitters, opens eventually onto questions that touch the deepest structure of what exists. How much energy is there? How long is it available? What does the geometry of spacetime permit? And somewhere beneath all of those questions, a quieter one, what would it mean to use it well? There is a kind of light that has been traveling longer than anything else we can detect. It does not come from a star. It does not come from a galaxy. It comes from a time before either of those things existed. Roughly 380 000 years after the Big Bang, the universe had cooled just enough for electrons and protons to settle into one another and form the first neutral atoms. Before that moment, the cosmos was a dense, opaque fog of charged particles, and light could not travel freely through it. Then, in a transition that took thousands of years, but was brief by cosmic standards, the fog cleared, and the light that had been trapped inside it was finally released. That light is still traveling. It fills the entire sky, arriving from every direction at once, so faint and so stretched by billions of years of cosmic expansion that it is cooled to just under 3 degrees above absolute zero. We call it the cosmic microwave background. It is the oldest light in the observable universe, a thermal glow left over from a time when everything that now exists was compressed into a space smaller than the distance between stars. When astronomers map it carefully, they find it is almost perfectly uniform. Almost. There are tiny variations, ripples of slightly warmer and slightly cooler regions, imprinted in those first moments. Those ripples became, over hundreds of millions of years, the seeds of everything, the filaments of gas that collapsed into the first stars, the first galaxies, the long, slow architecture of the universe we inhabit now. All of that structure grew from fluctuations smaller than anything we can hold in mind. And the first stars that formed from that collapsing gas were unlike any star burning today. They are called population 3 stars. And as far as we can tell, they contained almost nothing but hydrogen and helium, the two lightest elements, the ones that emerged directly from the Big Bang itself. There was no carbon, no oxygen, no iron, no silicon. The heavier elements that make up planets and oceans and the chemistry of living things, none of those existed yet. A population 3 star could not have hosted a rocky world. There was no rock. These were enormous stars, likely far more massive than the sun, burning hot and fast and brief. They lived for perhaps a few million years, then collapsed and exploded as supernovae, seeding the surrounding gas with the first traces of heavier elements forged in their cores. And then those enriched clouds collapsed again into a second generation of stars, slightly more complex, slightly more capable of hosting the chemistry that complexity requires. And then those stars lived and died. And the process repeated. Generation after generation of stellar birth and death, each cycle scattering more heavy elements into the interstellar medium, slowly enriching the raw material available to whatever might come next. The carbon in living cells, the calcium in bone, the iron that carries oxygen through blood, all of it was forged inside stars that no longer exist, scattered by explosions across distances measured in light years, gathered again by gravity into new clouds, new stars, new worlds. This took time, a great deal of time. Several generations of stellar death and rebirth were needed before the raw materials for something like Earth were sufficiently abundant, before the chemistry of complexity was even possible, which means that any civilization like ours could only have emerged after a long period of cosmic preparation, after the universe had done the slow, patient work of building the elements from which minds and machines and questions can be made. And yet, the universe is old enough that this preparation could have been completed long ago. In other places, any civilization that arose shortly after the first generation of suitable stars formed would have had over 13 billion years to develop, to grow, to spread. 13 billion years is a span so large that even the slowest conceivable expansion, even a civilization moving at a tiny fraction of the speed of light, could have filled a significant portion of the galaxy many times over. And still, as far as we can tell, the sky is quiet. That silence sits at the center of the Kardashev scale's deepest implications, not just as a puzzle about where other civilizations might be, but as a question about time, about what it means to exist early or late in the universe's long unfolding. We know now that the window for certain kinds of expansion is not permanent. The universe is not static. It is growing, and the rate of that growth is itself increasing, driven by something we call dark energy, a property of space itself that we do not yet fully understand. As that expansion continues, the galaxies beyond our local gravitational neighborhood are moving away from us, and they will continue to move away, faster and faster, until the light they emit can no longer reach us. The galaxies we can see today number in the hundreds of billions. In roughly 100 billion years, nearly all of them will have crossed beyond the horizon, not destroyed, not gone in any absolute sense, simply unreachable. Their light perpetually outrun by the expansion of the space it must cross to find us. What will remain visible, gravitationally bound, accessible, is the local group, the Milky Way and the few dozen galaxies held together by their mutual gravity, a small island in what will have become, from our perspective, an otherwise empty and featureless dark. A civilization that has not expanded beyond that island before the horizon closes will be confined to it, not by any failure of ambition or engineering, but by the geometry of the universe itself, by the fact that space, given enough time, becomes an insurmountable distance. This is one of the stranger gifts of cosmology, the reminder that even the largest scales of existence have edges, that the universe, for all its vastness, is also in some sense finite in what it permits. And so the question the Kardashev scale quietly poses is not only about power, it is about timing. A civilization that reaches Type 3, that spreads across its galaxy, that builds the infrastructure to use the energy of 100 billion stars before the cosmic horizon closes, has access to a universe, a civilization that does not may find itself, eventually, alone in a way that no amount of energy can remedy. There is something in that thought worth sitting with. Not with urgency, not with fear, but with a kind of quiet recognition that the universe has a shape, that it has a history stretching back to a fog of charged particles in a moment when light first traveled freely, that it has a future in which the lights, one by one, go beyond reach, and somewhere in the middle of that long arc, closer to the beginning than we might like to think, something on a small rocky world, built from the scattered remnants of dead stars, learned to ask how much energy a civilization might one day use, and began, very slowly, to reach. That reaching began long before us. The atoms in your body, the carbon, the oxygen, the iron moving quietly through your blood right now, none of them existed when the universe was young. The first stars had almost nothing to work with. Hydrogen, mostly a little helium, trace amounts of lithium. That was the entire periodic table of the early universe. No carbon, no nitrogen, no silicon, no iron. The architecture of biology simply did not exist. Those first stars, enormous and short-lived, burned through their fuel quickly. And when they died, when they collapsed and tore themselves apart in supernovae, they seeded the space around them with heavier elements for the first time. But one generation was not enough. The material had to cycle. Stars had to form from that enriched gas, live their lives, and die again, scattering more. And then again, generation after generation of stellar birth and death, each round leaving the cosmos a little more chemically complex, a little more capable of producing the raw ingredients for planets, for oceans, for the long, slow chemistry that eventually becomes something alive. This took time, billions of years of it. By some estimates, the universe may only have become genuinely hospitable to civilizations like ours. Civilizations built on rocky planets with liquid water and complex organic chemistry within the last few billion years, perhaps less. On a cosmic timeline, that is recent. And if that is true, if the conditions for complex life have only lately become widespread, then the silence we observe around us takes on a different quality entirely. It may not be a silence of absence. It may be the silence of an early morning before most of the world has woken. We search the sky and hear very little, and we wonder what that means. But perhaps what it means is simply that we are early, that the universe is still, in some sense, just beginning to produce the kind of complexity that asks questions about itself, that we are not alone in a vast graveyard of failed civilizations, but alone in the way that the first light of dawn is alone, not because nothing else exists, but because most of what will come has not yet arrived. There is something quietly comforting in that thought, and something humbling. Because it means the Kardashev scale, that elegant, precise ladder of energy use stretching from type 1 to type 3 and beyond, may be describing a future that is mostly still ahead, not just for us, but for the universe as a whole. And yet, the scale itself, for all its clarity, measures only one thing: energy. It tells us how much power a civilization commands, how many watts flow through its infrastructure, whether it has wrapped a star or filled a galaxy with its presence. It is a measure of reach, of scale, of physical dominance over the environment. But it says nothing about what a civilization does with that power, nothing about whether it is wise, or patient, or kind in whatever way kindness might mean across the vast distance of other minds. Nothing about whether it has learned to live within the rhythms of its world, or whether it has burned through everything available to it and left silence behind. Nothing about longevity, about whether a civilization that reaches Type 2 survives for 1,000 years or 1,000,000,000,000. Energy and wisdom are not the same thing. A civilization could, in principle, climb the Kardashev scale quickly and still be fragile, still be capable of the kinds of errors that end things. The scale has no axis for that, no measurement for the quality of choices made with all that power. And so perhaps the most advanced civilizations, the ones that have endured the longest, that have navigated the deepest stretches of time, are not necessarily the ones that shine the brightest. Perhaps they are the ones that learned, somewhere along the way, to be still, to use what they need, to move carefully through a universe that is, in the end, finite in what it offers, to exist not as a blaze of energy detectable across 100,000 light years, but as something quieter, something that has made its peace with the scale of things and chosen depth over expansion, patience over speed. We would not easily detect such a civilization. It might not want to be detected, or it might simply have no reason to announce itself, the way an old forest does not announce itself, but simply continues, quietly doing what it has always done. There is something in that image worth resting with. The idea that the silence of the cosmos might not be emptiness, that it might, in some places, be the silence of something very old and very settled. Something that has long since stopped reaching outward and begun instead to go inward, into computation, into experience, into whatever forms of depth become available when the urgent work of survival is finished. We cannot know. As far as we can tell, we have not yet heard from anyone. But we are also very young. By the Kardashev scale, We sit at roughly 0.73, not yet type 1, still drawing most of our energy from ancient sunlight compressed into carbon over hundreds of millions of years. Still learning, slowly and unevenly, to live on the flow of energy our star offers rather than the reserves our planet stored. We are, in the language of the scale, at the very beginning, and the universe is very old. Roughly 13.5 billion years old by our best measurements. Old enough that the light from its earliest moments has been traveling toward us for longer than the Earth has existed. Old enough that the first stars lived and died and were forgotten long before our sun ignited. And yet, for most of that time, the conditions for something like us may not have existed anywhere. The heavy elements were still being forged. The rocky planets were still accumulating. The chemistry was still becoming possible. So perhaps the universe is old, and we are early, and the long conversation between civilizations, if it ever happens, has not yet truly begun. Perhaps we are something like the first words of a very long story. Not the end of something. Not a rare exception in a silent cosmos, but a beginning. One of the first instances of the universe becoming aware of its own scale, its own age, its own strange and patient beauty. The Kardashev scale gave us a way to think about that, a framework built from physics and energy and the quiet logic of what is possible. It began as a tool for estimating alien radio transmitters and became something larger, a map of what civilizations might become, and a mirror in which we can see how small we still are and how much of the journey remains. Nikolai Kardashev wrote his paper in 1964, a single scientist, at a desk, somewhere on a small planet orbiting an unremarkable star in the outer reaches of one galaxy among hundreds of billions. And he looked up at all of it and tried to measure it. That, too, is a kind of reaching. And tonight, you have followed that reach as far as it goes, out to the edge of the observable universe, forward to the dimming of the last accessible galaxies, back to the first scattered atoms of heavy elements drifting through the dark after the death of ancient stars. You can let all of that settle now. The scale, the silence, the slow accumulation of complexity across billions of years. It is all still there. The universe is not going anywhere, and neither are you. Just here, quiet, breathing slowly. Part of the same matter that was forged in stars and scattered across the dark and found its way, after a very long time, to this moment, still and listening. There is something worth sitting with before sleep takes you fully. The universe you have been traveling through tonight, the one measured in watts and light years and billions of years, is also, at its smallest scale, deeply strange. Not strange in a way that disturbs. Strange in a way that quietly dissolves certain assumptions you may have carried without knowing you were carrying them. The assumption, for instance, that two things separated by distance are simply separate. It turns out that is not always true. Quantum mechanics, the physics of the very small, describes a phenomenon called entanglement. And entanglement is, as far as anyone can tell, a genuine feature of the universe, not a trick of mathematics or a gap in our understanding. When two particles interact in certain ways, they can become entangled. Their properties become correlated in a way that persists even after the particles have moved apart, even after they are on opposite sides of a room, or a city, or, in principle, a galaxy. Albert Einstein found this deeply uncomfortable. He called it, in German, spooky action at a distance. He believed it pointed to an incompleteness in quantum theory, not a truth about the world. He thought there must be some hidden information, some variable we simply had not found yet, that would restore a more sensible picture of reality. He may have been the greatest physicist who ever lived. And on this, the evidence suggests he was wrong. Not carelessly wrong. Thoughtfully, carefully, persistently wrong. The kind of wrong that takes decades and extraordinary experiments to confirm. In 1964, the same year, Nikolai Kardashev published his energy scale. A physicist named John Bell derived a mathematical theorem. Bell showed that if Einstein's intuition were correct, if entangled particles were simply carrying hidden instructions from the moment they separated, then measurements of those particles would obey certain statistical limits. These limits are now called Bell inequalities. And experiment after experiment has shown that nature violates them. The correlations between entangled particles are stronger than any hidden variable theory can explain, stronger than any pre-existing agreement between the particles could account for. The particles do not seem to be carrying secret instructions. They seem to be genuinely, irreducibly connected. The first serious experimental tests were conducted in the 1970s and early 1980s. Alain Aspect and his colleagues in Paris performed a series of careful measurements on pairs of entangled photons. They found violations of Bell's inequalities, consistent with quantum mechanics and inconsistent with Einstein's preferred picture. Later experiments closed one loophole, then another, ensuring the detectors were far enough apart, ensuring the measurement settings were chosen randomly and quickly enough that no signal between the particles could explain the results. Each refinement made the conclusion harder to escape. By 2015, experiments had closed the most significant loopholes simultaneously. The correlations are real. They are non-local. They cannot be explained by anything traveling between the particles at the moment of measurement. And yet, no message is sent. This is the part that takes a moment to settle. When you measure one entangled particle and find a particular result, the distant particle's measurement outcome is correlated with yours. But you cannot use this to send information. You cannot choose what result you get. You cannot control the correlation in a way that carries meaning to someone far away. The connection is real, but it is not a channel. It is more like a shared fact that neither particle possesses alone, and that only becomes visible when two distant observers compare their notes. After the measurements, after the comparison, the correlation is there, quietly, in the data. It does not violate relativity. It does not allow anything to travel faster than light. It simply reveals that the universe's accounting of certain properties is not done locally, the way we might have expected. Two particles, once entangled, are in some sense still one system, no matter how far apart they drift. There is a quietness to that idea, if you let it rest without forcing it into familiar shapes. Physicists have spent decades debating what entanglement means for our picture of reality. Whether it implies that space itself is less fundamental than the correlations woven through it, whether the separateness of distant things is, at some deep level, an approximation. These questions remain genuinely open. What is not open is the experimental record. Entanglement is not a philosophical speculation. It is a measured, reproducible, precisely characterized feature of the physical world. And it has become useful. Quantum information science, a field that barely existed 40 years ago, now uses entanglement as a resource, the way an earlier civilization might have learned to use fire, or magnetism, or electricity. Quantum cryptography uses entangled particles to distribute encryption keys in a way that is, in principle, impossible to intercept without detection. Any eavesdropper disturbs the entanglement, and the disturbance is visible in the statistics. Quantum computing uses entanglement to allow certain calculations to proceed along many paths simultaneously. in a way that classical bits cannot replicate. The machines are still small and fragile, prone to errors from the slightest environmental interference. But they exist. They run. They solve certain narrow problems faster than any classical device. Quantum teleportation, a term that sounds more dramatic than it is, uses entanglement to transfer the complete quantum state of one particle to another. Distant particle, not the particle itself, not faster than light, but the information describing its exact quantum condition, transmitted through a combination of entanglement and an ordinary classical signal. It has been demonstrated in laboratories, between buildings, between islands, between a ground station and a satellite in orbit. The satellite experiments, conducted by a Chinese research team in the 2010s, transmitted entangled photon pairs across more than 1,000 kilometers. The correlations survived the journey through the atmosphere and the vacuum above it. 1,000 kilometers is, by the scale you have been traveling tonight, an almost imperceptibly small distance. And yet, it was, for entanglement, a proof of principle. Entanglement also appears in precision measurement. Atomic clocks, gravitational wave detectors, and other instruments can use entangled states to achieve sensitivities beyond what classical physics would allow. The correlations between particles reduce certain kinds of noise, allowing measurements of extraordinary delicacy. The gravitational wave detectors that first observed two black holes merging in 2015 used squeezed light, a quantum technique related to entanglement, to push their sensitivity past classical limits. They were listening for a ripple in space-time smaller than 1/10,000th the diameter of a proton. And they heard it. Quietly. In the data, there is a thread running through all of this, if you are still following it in the soft edge of sleep. The universe, at its largest scale, is vast beyond any comfortable imagining. Hundreds of billions of galaxies, each containing hundreds of billions of stars, spread across a volume that light has been crossing for nearly 14 billion years. And at its smallest scale, the universe is strange in a different direction. Particles that share a history share something more. A correlation that distance does not dissolve. A connection that no hidden mechanism has yet been found to explain. The Kardashev scale measures what a civilization might do with energy. But energy, at its root, is a property of particles, of fields, of quantum systems that do not always behave the way our intuitions expect. Any civilization that reaches Type 2 or Type 3 will have had to reckon with this strangeness, will have had to learn to use it, the way we are only beginning to learn. Perhaps they already have. Perhaps the most advanced forms of communication or computation in the universe run not on radio waves or laser pulses, but on correlations woven into the fabric of space itself. We do not know. As far as we can tell, no one does. And that is all right. Not knowing, held gently, is its own kind of rest. The questions are still there, the experiments are still running, the data is still accumulating, quietly, in laboratories on a small planet orbiting an unremarkable star. And you are here, still, breathing slowly. Part of the same quantum world that Bell described, and aspect measured, and no one has yet fully understood. Connected in ways that distance does not entirely undo. To all of it. And so we return, quietly, to the scale itself. Nikolai Kardashev was a Soviet astronomer. He published his paper in 1964. He was not trying to describe humanity. He was trying to estimate how powerful an alien radio transmitter might need to be, how much energy a civilization would have to command to make itself heard across the distances between stars. He drew 3 lines. A Type 1 civilization uses all the energy available on and delivered to its home planet. A Type 2 captures the full output of its star. A Type 3 draws on the energy of an entire galaxy, roughly 100 billion stars, each quietly burning. These were not predictions. They were coordinates, a way of placing civilizations on a map whose full extent we have never seen. Carl Sagan later extended the scale to include fractional values, civilizations between the whole types. By that measure, Earth sits at approximately 0.73. Not yet Type 1, still climbing. The Sun delivers to this planet each day about 10,000 times the energy we currently consume, all of it arriving whether we use it or not, warming the oceans, driving the winds, falling on every surface, absorbed and re-radiated in the long, slow breath of the atmosphere. We are not short of energy. We are short of reach. A Type 1 civilization would command roughly 10 to the 16th watts. Continuously, a Type 2, 10 to the 26th. The full output of a sun-like star, held and directed. A Type 3, 10 to the 36th watts. The luminosity of a large galaxy, flowing through whatever structures such a civilization had learned to build. Freeman Dyson imagined one such structure in 1960. Not a solid shell, which would require more material than all the planets of our solar system combined, but a swarm, thousands or millions of collectors in orbit around a star, intercepting its light, converting it, re-emitting the waste as infrared radiation. That infrared excess would be detectable, a technosignature, a sign not of biology but of engineering, written in heat. Astronomers have searched catalogs of infrared bright stars for exactly this kind of anomaly. So far, nothing conclusive has been found. The star, sometimes called Tabby's star, dimmed in irregular patterns that briefly suggested something artificial. Later analysis attributed the dimming to dust and cometary debris, not engineering, but the search continues, quietly, in the background of other work. There are other proposed structures. A Matryoshka brain, nested computational shell surrounding a star, converting all its energy into processing power. Its waste heat would still be visible, still infrared, still, in principle, findable. Stellar lifting is another proposal, extracting hydrogen and helium from a star's outer layers to slow its fusion rate, to extend its life. A sufficiently advanced civilization could, in theory, tend its star the way a gardener tends a tree, pruning it gently across millions of years. These ideas are speculative, but they are grounded in physics that does not forbid them. They are the kinds of things that become possible when energy is no longer a constraint. And yet, no one has announced finding them. The galaxy is old, roughly 13 billion years old. A civilization spreading at even 1% of light speed could cross it entirely in about 10 million years. 10 million years is less than 1/10 of 1% of the galaxy's current age. The silence is not easily explained. Enrico Fermi reportedly asked the question during a lunch conversation in 1950, not in a paper, not in a lecture, just a quiet question over a meal. If civilization should be common, where is everyone? The Drake equation, formulated in 1961, tries to estimate how many communicating civilizations might exist in the Milky Way. Most of its terms remain deeply uncertain. The answers range from less than 1 to millions, depending on what you assume. Some have proposed that the conditions enabling complex life are extraordinarily rare. Earth's large moon stabilizes its axial tilt, moderating climate across geological time. Jupiter may have shielded the inner planets from a higher rate of large impacts. Earth sits within the galactic habitable zone, far enough from the dense and radiation-intense center to allow stable chemistry. Perhaps all of this is unusual. perhaps it is not. The Great Filter is the name given to whatever step in the development of spacefaring civilizations is hardest to pass. If that filter lies behind us, in the emergence of life, or of complex cells, or of something else we have already survived, then we may be among the first. If it lies ahead, it is a barrier that has stopped nearly everything before it reached Type 2. The discovery of simple microbial life on Mars would be, paradoxically, unsettling. It would suggest that life begins easily, which would push the filter forward, closer to us, still waiting. Self-destruction is one proposed answer to the silence. War, ecological collapse, technologies that outpace the wisdom to use them. The dark forest theory proposes something colder, that civilizations hide deliberately, knowing that any civilization detected may be destroyed by others who cannot afford to take the risk. The zoo hypothesis offers a gentler version, that we are observed and left alone by those who have decided not to interfere. The simulation hypothesis offers something stranger still, that advanced civilizations may exist entirely within computational substrates, invisible to any telescope. We do not know which of these, if any, is true. What we do know is that our own radio bubble, the sphere filled by 100 years of transmitted signals, is only about 200 light-years across. It contains a few thousand stars out of 200 to 400 billion. We have barely whispered. The James Webb Space Telescope can now analyze the atmospheric chemistry of distant planets. Nitrogen dioxide at concentrations above natural levels could indicate industrial activity. A technosignature written not in radio waves but in air. Future instruments may read it. A Type 2 civilization could use the gravitational lens of its own star as a natural telescope, imaging planets around other stars in fine detail. A Type 3 might use the gravitational lens of the galactic core to observe or communicate across the full diameter of the galaxy. Globular clusters have been proposed as favorable locations for long-lived civilizations. Their stars are on average 10 billion years old. Any life there would have had a multi-billion-year head start, though their low metallicity, fewer heavy elements, may have made rocky planets and complex chemistry harder to assemble. The universe itself sets an upper bound. The total luminosity of the observable universe is roughly 10 to the 49th watts. A hypothetical Type 4 civilization would harness all of it. Dark energy, which drives the accelerating expansion of space, represents a reservoir beyond that, one that no known physics can yet approach. And the universe is expanding. Galaxies beyond a certain distance are already receding faster than light, permanently unreachable. In roughly 100 billion years, the Milky Way and its local group will be the only galaxies visible from here. The rest will have crossed the horizon. A civilization that does not reach Type 3 before that horizon closes may be confined permanently to a single gravitational island. The first stars contained almost no heavy elements. They could not have hosted rocky planets. The elements needed for chemistry and biology were forged inside stars and scattered by supernovae across billions of years. Life as we know it required several generations of stellar death before the raw materials were sufficiently abundant. The universe may have only recently become hospitable enough for civilizations like ours to emerge in significant numbers. If that is true, if we are among the first, then the silence is not a paradox. It is simply the quiet of an early morning, before much has begun. The Kardashev scale measures energy, only energy. It says nothing about wisdom, nothing about what a civilization chooses to do with what it commands. Perhaps the most advanced civilizations are not the loudest. Perhaps they are the most patient. We are, by the scale's measure, very young. The universe is very old. And still, mostly listening, as are you, breathing slowly, somewhere between waking and whatever comes next. The questions remain, held gently.